Hello everyone. Today's presentation is on the Karhunen Loeve transform or shortly KL transform in image processing. The KL transform is a powerful tool used in data compression, feature extraction and decorrelation of signals, especially in multispectral and hyperspectral image processing. To understand the KL transform, we must first understand eigenvalues and eigenvectors. For a square matrix C of size n by n, a scalar lambda is called an eigenvalue if there exists a non-zero vector E such that C times E equals lambda times E. The vector E is called the eigenvector corresponding to that eigenvalue. Now consider a population of random vectors as shown. Each component xi may represent the gray level of pixel I. This population may arise from pixel-wise data collected across an image forming such vectors. An example of such vectors is pixel values recorded in multiple spectral bands. For instance, in remote sensing or multiple spectral imaging, a single pixel location might have multiple intensity values across various wavelength channels. The mean vector of the population is defined as the expected value of x. The covariance matrix C is the expected value of the outer product of the deviation of x from the mean. When we have m such random vectors, we can compute the empirical mean and covariance matrix as shown in the figure. Let matrix A consist of the eigenvectors of the covariance matrix C arranged such that the first row corresponds to the largest eigenvalue and the last to the smallest. Then the KL transform of vector x is defined as y equals a times x minus the mean vector. The transformed vector y has zero mean. The covariance matrix of y is given by a times cx times a transpose. This results in a diagonal matrix where each diagonal element corresponds to an eigenvalue. Thus, the KL transform decorrelates the input components. To reconstruct the original vector x from its transform, we use the inverse KL transform, that is x equals a transpose times y plus mean vector. If we only keep the k eigenvectors corresponding to the largest eigenvalues, we use matrix AK, which is k by n. The resulting y vector is now k dimensional. The approximate reconstruction is given by AK transpose times y plus m. When we use only k components, we achieve compression but also introduce error. The mean square error between the original vector and the reconstructed vector is the sum of eigenvectors from k plus 1 to n. This expression quantifies the approximation loss. Despite its advantages, the KL transform has limitations. Its basis functions depend on the covariance matrix. So they must be recomputed for every image. Perfect decorrelation is rare due to the non-ergodic nature of the images. Also, there is no fast algorithm for computing the KL transform. This is a reminder that the x vectors used in these examples represent pixel values from different spectral bands or channels. This is typical in airborne imaging systems where data is collected across a wide range of wavelength. Here we see 6 spectral images from an airborne scanner, each corresponding to a specific wavelength band. These include visible blue, green and red as well as near infrared, middle infrared and thermal infrared. These are the original input channels before applying the KL transform. After applying the KLT to the original 6-channel image data, we obtain 6 principal components. Each component represents a projection of the original data along an eigenvector direction, with the first component capturing the most variance. This table shows the eigenvalues corresponding to the 6 principal components. The first component has the largest eigenvalue, 10344, indicating its capture the most variance, and the sixth component has the least with a value of 31. You can observe how the essential information is concentrated in the first few components. The slide shows the original 6 spectral images on the left and the 6 principal components derived using the KL transform on the right. This figure shows the results of the constructing the 6 multispectral images from the 2 principal component images correspond to the largest eigenvalues. The first 5 images are quite close in appearance to the originals in the figure 1. But this is not true for the sixth image. The reason is that the original sixth image is actually blurry, but the 2 principal component images used in the reconstruction are sharp. Therefore, the blurry detail is lost. Thank you for your attention. This concludes the presentation on the KL transform in image processing. I hope it gave you a clear understanding of its principles, application, and limitations.